Okay, so welcome. I think I said I'd start at 1:03, but if we start 1 minute early, I don't think that's too bad. So anyway, so last time we're almost done with chapter 1 finally. I know it seems a little weird the way that the material is split up, but we've been on chapter 1 for a long time. But chapters 2 and 3 are really short, so we will be in chapter 4 before you know it. So anyway, on to and one to oneness. Essentially, what we're going to do is basically use all the stuff that we've done in chapter 1. We're going to apply it over and over again in different language throughout the rest of the course. Even when we get to chapter 4, we're just going to be doing like slightly more abstract versions of that. But anyway, so maps being onto and one-to-one. Kind of the best intuitive way of thinking about this is through pictures. So to talk about a map that's onto, this is if every single B in the codomain is the image of at least one X in the domain, i.e. For every single B, so if T is onto, then every B in Rm comes from some X in Rn, i.e. T of X is equal to B. That is, for every single B, there is some X. There exists some X such that T of X is equal to B. Okay, so what this is saying is that the range of T fills out Rn. Okay, so this says that the range of T fills out Rm. What do I mean by that? So if I have a map T, here's my Rn, it's a floppy space like this, and I have T pushing stuff to Rm. If my range of T looks like this, what is the range of T? Well, the range of T is the collection of all vectors B that come from something over here in Rn. So, if something is in the range of a transformation, that means there exists some X in Rn such that T of X is equal to B. Okay. So then what does it mean for something to be here? All right, so let's say here is, we'll say here's B sub 1, and here is B sub 2. So if B sub 2 lies in the range of T, that means there exists, so this symbol means there exists. Okay, so there exists X in Rn such that T of X is equal to B2. Okay, that's what it means to be in the range. If something is in the codomain that's not in the range, that means there is no X such that T of X is equal to this B sub 1. So the fact that there is this difference here between the range and the codomain, remember, I made a big point of saying that the codomain and the range are not the same. Okay, sometimes they're the same, sometimes they're equal, but in general they're not. So the fact that this shaded region exists, that there is some difference between the codomain and range. The range always sits inside the codomain. Okay, but the fact that there's this difference means that T is not onto. So this T is not onto. Why? Because there's vectors here that lie outside the range of T even though they're in Rm. So they're in the codomain, but they're not in the range. That's not possible for an onto map. Because for an onto map, every single vector in the codomain is the image of at least one X in the domain. Okay, and so what does it look like if T is onto? So if T is onto, what the picture looks like is you got your Rn here. Okay, and here's your map T. Here is Rm, but Rm is actually equal to the range of T. Okay. So, oh, I'm a little bit off. So if I tried to draw in the range of T, it actually coincides exactly with Rm. Okay, that's the point. All right. So if T is onto, Rm is equal to the range of T. Okay, that's another way of defining onto. All right. So there is not a difference between the codomain and the range. Okay. Now, what about T being 1 to 1? So T being 1 to 1, what does it look like if T is not 1 to 1? Maybe that's the thing to ask first. So here's our map T, mapping from Rn to Rm. Here's, say, some points, and here's some points in the codomain. We'll say they're in the range because they're going to get mapped to. Okay, now let's remind ourselves what 1 to 1 means. So 1 to 1 means that each B in the codomain is the image of at most one X. Okay, and so I'm going to draw in 3 points here. So let's say that this point comes from a single point. This point comes from like 2 different, 3 different, maybe many different points. Okay. This is not hit at all, but that's not a problem in general. Okay. But this point is a problem. This point has multiple x's in the domain that get mapped to it. It is not 1 to 1, it is many to 1, right? Because many x's over here go to the same one image point. Okay, so that's T is not 1 to 1. All right. So what does it look like if T is 1 to 1? So here's my domain. Here's T. Here's my codomain. And let's say here's my range. So here's range of T. So I have points that are not in the range of T. Nothing goes to them. But for all my points that are in the range, they all get mapped to by a single point. That's where the name 1 to 1 comes from. Okay. All right, so this T is 1 to 1. Notice it doesn't matter that you have a point here that is outside the range of T. Why? Because the definition of 1 to 1 says that every B in the codomain is the image of at most 1. So it can't be more than 1, but it's perfectly fine if there's 0 points that map to it. Okay. This is the key distinction that tells you that being 1 to 1 and being onto has nothing to do with each other. Okay, so note, 1 to 1 and ontoness are not related. This is very, very important. Okay, you cannot find one from the other. So note, T being 1 to 1 or onto. Actually, that's a bad way of phrasing it. Let's phrase it like this. T being 1 to 1 has nothing to do with whether or not T is onto. Okay, so this is very important. And vice versa, right? So T being onto has nothing to do with it being 1 to 1. Okay. I.e., there are examples fact, you're going to have to come up with these. So there are examples of t such that t is 1-to-1 and onto. 2, t is neither 1-to-1 nor onto. 3, t is 1-to-1 but not onto. And 4, t is onto but not 1-to-1. Okay, all 4 of these are possible. Okay, so that exactly means that these have nothing to do with each other. They are 2 separate properties. There's no way to derive one from the other. Okay. Now, it turns out that, as I said, finding the range of a map in general is kind of hard. So I want a better, more efficient way of being able to say whether or not some given t is 1-to-1 or onto. So question, how do I know? Right? Question, can I quickly deduce whether t is 1-to-1 or onto? These are very important properties to have. The reason they're important is here's a quick way of giving you the full rundown. If you may have seen being 1-to-1 and onto as a property of functions, not general transformations or not matrix transformations. When functions are 1-to-1 and onto, they are a very, very nice sort of function that basically serve as an equivalence between the objects you're talking about. Okay. So for us, this is going to define what are called isomorphisms. So we'll talk about that in chapter 4. But these are really, really nice. So being 1-to-1 and being onto it's very nice properties to have. So anyway, is there a way where I can quickly deduce whether or not these things are 1-to-1 or onto? The answer is I have the following 2 theorems. That tell me exactly what I want to hear. So what are my following 2 theorems? So there's theorem that addresses being 1-to-1. So let t from Rn to Rm be a linear transformation. Then t is 1-to-1 if and only if the equation t of x is equal to the 0 vector has only the trivial solution. Okay. What is this? What does this mean? Right. Where does this come from? So quickly, without actually proving where this comes from, you use the fact that t is a linear transformation. Basically, what you say is, well, if t is 1-to-1, that means whenever 2 vectors u and v are different, t of u and t of v are different, right? So, okay, we can quickly do this, right? If u, if u is not equal to vector v, but t of u is equal to t of v, then t of u minus t of v is equal to the 0 vector. Using the fact that t is linear, this means that t of u minus v is equal to the 0 vector. And so, if this is non-trivial, this has a non-trivial solution, right? i.e., T of x equals 0 has a non-trivial solution. But what did we assume? We assumed that u is not equal to v, but t of u is equal to t of v. What's that? That's assuming that t is not 1-to-1. So we showed that if t is not 1-to-1, then this equation has a non-trivial solution. This is something called proving the contrapositive. So we prove the contrapositive of the statement. Contrapositive of a statement and a statement have the same logical values. So we're done with some tidying up here because I technically didn't do one of the other directions. Okay. Right, so someone mentioned linear independence in the comments, so that's exactly what this means. So actually, I can loop this into another theorem that explains both 1-to-1 and onto. So this is a very important fact here. So I have a theorem, very important. So this is, if you like, this is the characterization of a transformation being 1-to-1 and onto. So I'll give it a name here. Okay, so here's a theorem. Let T from Rn to Rm be a linear transformation. Okay. Let A be its standard matrix. Okay. So say we found the standard matrix for T, we've called it A. Then 1. T maps Rn onto Rm if and only if the columns of T, or the columns of A, span Rm. Okay. And secondly, T is 1-to-1 if and only if the columns of A are linearly independent. And now we see how we have given ourselves here a criterion that allows us to tell whether or not a given linear transformation is 1-to-1 or onto directly from the matrix for the transformation. Okay. All right. So this is how we know. Okay. All right. So it seems like there's no more questions about that. So this is how it goes. All right, this is actually how we do this. Now let's do a quick example, then we'll move on. So let T of x of 1, x of 2 be the expression given us 3 x of 1 plus x of 2 in the first slot. In the second slot, it's 5 x of 1 plus 7 x of 2. And in the last slot, it's x of 1 plus 3 x of 2. Okay, so 1 is T 1-to-1, and question 2 is T onto. That is, does T map R2 onto R3? Right, so note that T is a linear transformation from R2 to R3. Okay. So first of all, in order to answer these questions, it's always best to be working with the standard matrix for T. What's the standard matrix for T? I can actually just read the standard matrix off here. I can see it. So the standard matrix for T is 3, 1, 5, 7, 1, 3. right? So here's my A. Okay. Okay. So here's a question. So first of all, how do I answer this thing being 1 to 1? I just had it on the screen here. So it's 1 to 1 if and only if the columns are linearly independent. Are the columns linearly independent? The columns are two vectors, a sub 1 and a sub 2. It's those two vectors. So 3, 5, 1, 1, 7, 3. When I'm thinking about a set of vectors and I'm asking whether or not they're linearly independent, well, if I have a set of two vectors, what's the only thing I have to do to check linear independence? Well, if it's a set of two vectors, they're linearly independent so long as they're not scalar multiples of each other. Well, we can just check. 3 and 1, I would have to multiply this one by 3. Okay, so if I multiply this by 3, multiplying 7 by 3 would give me 21, but that's not 5. Right? Multiplying 3 by 3 is 9, which is not 1. So these are not scalar multiples, right? So A1 and A sub 2 are linearly independent. Since they're not scalar multiples, because it's just a set of two vectors. Thus, these columns are linearly independent. Thus, T is 1 to 1. So, is T 1 to 1? Yes. Is T onto? That is, question. Do the vectors a sub 1, a sub 2 span R3? Well, later on in the course, we will have a quick answer to this, which is no, because there's only two of them and you need at least 3. Okay, but we don't have that in our toolbox yet. So then how do I say something about this? Well, there's a theorem. See if we can look up this theorem. It's a theorem that I didn't give a number. It's coming from the textbook here. Let me see, where is it? I'm flipping through. We're almost there, I think. Here we go. Theorem 4 from the textbook, which I stated as the first theorem that had the following are equivalent, right? TFAE. And so there were ABC parts that were, this is a little blurry. Let me put it down here. So there were A, B, and C parts that I wasn't that interested in because that was actually the stuff that I wanted. So for instance, the columns of A span Rm. That's what I want. I want to know, when do the columns of A span Rm? So these are all logically equivalent. So then when any of these other things happen, that's when the columns of A span Rm. That happens when A has a pivot position in every row. Okay. So let's go back here. If A has a pivot position in every row, then I'm good, but can A have a pivot position in every row? Well, no, right? Why? Because it has 2 columns and 3 rows, right? So, note, A cannot have a pivot position in every row. Thus, its columns cannot span R3. Thus, T is not onto. Okay, so that's an example of how to use these things. Okay. Questions. I don't see any, so I will move on. But that's how this goes. Okay, now let's get on to the next topic. So we are finally in chapter 2, which is basic matrix multiplication, or, well, yes, that's true, but basic matrix algebra. Okay, so some basics. So one, there's some notation I've already kind of, sort of introduced you to, but here's a quick refresher. When I write a matrix, and I say a matrix is size m by n, this is a rectangular array. Someone asked, will we be having an exam on chapter 1? Yeah, I still haven't posted the schedule. I'll try to do that tonight. I keep forgetting to post the lecture schedule. Since I'm posting all these videos, the schedule is kind of easy because it's just chronological, following the textbook sections. But I'll try to post the lecture section so you'll at least know in advance. And also, I had mentioned that I moved to having 2 midterms instead of 1, so your first midterm is still a couple weeks off. So it will be your first midterm will be not just on chapter 1. Traditionally, that's how it goes. You have a midterm only on chapter 1, but I'm gonna have your midterm will be on chapters like 1 through chapters 1 through like 3 at least. So anyway, I'll like I said, we'll get to that. We'll get to that soon enough. I'll post a schedule and when your first exam is going to be, but you still got a while. Okay, so anyway, when I say that I have an m by n matrix, I mean a rectangular array. And so let's write out the following way of labeling this. So I have A11, A12, A13, and so on, all the way out to A1n. I have A21, A31, and so on, all the way down to AM1, AM2, going across the last row, all the way to A sub mn. So that's how this goes. This can be written in the following way. This is A sub ij, m by n. So a lot of times you'll see this written as something. I'm not going to write it like this because it's too long-winded. So you'll say like j between 1 and I between 1 and m, and j between 1 and n. So these are 2 subscripts. You've seen this before. So A sub 1 means it is the entry in the first row, first column. A sub 2 is the entry in the first row, second column. A sub 3 is the entry in the first row, third column, and so on. So A sub 1n is the entry in the first row, nth column. A sub mn then is the entry in the mth row and the nth column, right? So this is the ijth entry. A sub ij is the ijth entry. This is how this is said. So, A sub ij is the ijth entry of A. Okay, i.e. the entry in the ith row and jth column. Okay. So it is useful to familiarize yourself with this. Okay. All right. So categorizing this in maybe a nicer way. Typically, of course, we're not going to write out a bunch of this unless we really have need for all these entries. So the way that we're going to do this is we're going to say, well, I'm going to view these as column vectors all the way out to my last. So I'm actually going to view it as a collection of n columns, right? So I'll label these A sub 1, A sub 2, A sub 3, all the way out to A sub n, so that another way of writing this A, this is something you've definitely seen before. So this is writing it as the matrix that has these vectors as its columns. Okay, so these are the columns of A. So this is just another way of doing this. Okay, so m rows, n columns. This is notation we're going to be using for the rest of the semester, so you have to familiarize yourself with this. It's going to be a long exam. No, I mean the exam won't be that long, and I mean it's a take-home exam anyway, so. So you're not gonna give it to you and say do this in 50 minutes or something. Okay. Now, I could go ahead and go back here for a second, just summing some things up. A diagonal, or the diagonal entries are these. All right, so A11, A22, A33, and so on, all the way out to A, whichever of these you hit first, right? So this is not guaranteed to be on the diagonal. Maybe it's a little bit misleading because the diagonal starts in the upper left, but it doesn't necessarily terminate here. So maybe I should do something like this instead. Okay. Now for some matrices, for square matrices, the diagonal will be, the last term in the diagonal will be this bottom right corner. But we'll say all the way up to A sub kk. All right. These are the diagonal entries. Okay, and a diagonal matrix. Oh, I don't want to use the capital A there. It's a little bit confusing. A diagonal matrix is one that has all entries 0 off the diagonal. And diagonal entries can be anything. So the 0 matrix, for instance, is a special matrix. So there's the 0 matrix. So I'll write that as 0 sub mn. This is the m by n matrix with all entries 0. Okay. The n by n identity matrix we've already seen. So we'll write this as I sub n by n. This is the matrix that has diagonal entries 1 and all other entries 0. So this is a diagonal matrix. Here's an example of a diagonal matrix. So the column index doesn't come first. We're using the column vectors just because we always treat vectors as columns. Could we treat vectors as rows instead? Yes, we could. We just don't. So that's why. Like, could you do an entire matrix theory where you've just swapped them? Yeah, you could do that. But we're going to do it this way. An identity matrix, or the identity matrix, is an example of a diagonal matrix. The entries on the diagonal are whatever. In this case, they're all 1, and off the diagonal, they're all 0. So this is also an example of a square matrix. So a square matrix is exactly what it sounds like. It's not rectangular. That is, m is equal to n. A matrix A sub m by n is rectangular. Right? If m is not equal to n. It's a little bit confusing because this is not really what I intend by rectangular matrix. Typically, when you say rectangular matrix, it's fine if it's a square matrix. So maybe I don't want to say this. The default assumption is that you have a rectangular matrix that's actually rectangular. But sometimes you'll just say A is an m by n matrix and it's rectangular, basically as kind of a general position type thing. But this is typically what's implied. So just so it's not too confusing. This is what we're talking about. Identity matrices can only be square. That's right. Yeah. Okay. There's certain things we're going to talk about in this course that only apply to square matrices. I'll be very clear what those things are when we get to them. Okay. So let's define some basic operations that you can do with matrices. So basic matrix operations. So we can add, right? In fact, rather than define these things like entry-wise, let's just do an example. So we can add and subtract and scalar multiply matrices easily. So to see this, like I said, rather than write out like a formal definition, so let's let A be the matrix. I'm reading row-wise, so 4, 0, 5, minus 1, 3, 2. Let B be the matrix 1, 1, 1, 3, 5, 7. Let C be the matrix, say 2, minus 3, 0, 1. Okay. So then what do we, how do we define A plus B? So we define it in the stupidest way possible, where we think of taking the matrices A and B, lining them up perfectly, and then summing the results. This is similar to vector addition, right? This is what you did for vectors. You lined up those two things and just added the entries. So a matrix is really, what is a matrix, right? I remember some student, was asking a question about this, and when I answered, it kind of blew their mind that they thought about it like this. You know what a vector is, right? So what's a matrix? It's just a vector of vectors, right? It's just a vector, and in every slot you have another vector of some size, right? If the number of vectors you have and the vectors in question that are in that number of vectors are the same number, then you get a square matrix. If not, you get a rectangular one, right? So any rectangular array in general, right, it's a vector of vectors, right? Anyway, so what A plus B, I'm lining them up here and just adding the entries literally component by component, right? So basically the sum here would be so A sub ij plus B sub ij would be equal to the matrix whose ijth component is A sub ij plus B sub ij. Right? Okay, so this is what my matrix is. So I'm just adding component by component. So 4 plus 1 is 5, 0 plus 1 is 1, 5 plus 1 is 6, minus 1 plus 3 is 2, 3 plus 5 is 8, and 2 plus 7 is 9. Right? But note, A plus C is undefined. Right? Okay. So A plus C is undefined. Someone's asking, could you have a matrix of matrices? Yeah, but it's just the same as doing it this way. So once you move to many dimensions, you can actually show this. This is something you can think about later. So for instance, you could even have three-dimensional matrices if you wanted to. So say that here's like a slice of my matrix. I could define a three-dimensional array of numbers, right? So then I would have different slices. So maybe I'd have 10 slices here. This is the bottom slice, and then I have slices. So it's a three-dimensional matrix. You can do it that way, but actually you can show that there's a way you could do it in 2D that's identical to that. It's actually equal to the same thing. So once you're doing it this way, this is the most general form. So it doesn't matter if you move into 3 and 4 dimensional matrices, you're doing the same thing. Okay, so anyway, so A plus C is undefined, right? So to add two matrices in this way, they have to have the exact same size, right? So note, to add or subtract matrices A and B, they must have the exact same size. Okay. Now, it turns out that adding and subtracting matrices is pretty much useless, but we'll keep doing it. So what's A minus B? What is A minus B? Well, 4 minus 1 is 3. 0 minus 1 is minus 1. 5 minus 1 is 4. Minus 1 minus 3 is minus 4. 3 minus 5 is minus 2. And 2 minus 5 is minus 5. There we go. Okay. All right, so adding and subtracting matrices is exactly like this. Okay. No, they don't. They have to have the same m and n, but n and m do not have to be the same, right? In fact, A and B are both rectangular matrices. They're not square. So A is 2 by 3, and B is 2 by 3. But C is 2 by 2, right? For C to be addable to A or B, it would have to also be a 2 by 3 matrix. Okay, so when you add or subtract matrices, you begin with a size and you end with the exact same size. Okay, that's important. Now, so that takes care of adding and subtracting matrices, and really, once you've seen one example, you've seen them all. We're not going to be doing this that much in this class because, as it turns out, unlike with numbers, adding and subtracting matrices is pretty much useless. So, not much point in adding or subtracting matrices. That might come as a shock to you that like a basic operation such like as addition is useless, but that's the case. Now the zero matrix performs the role of 0 for addition, like you might expect. So let's look at scalar multiplying a matrix. So scalar multiples of matrices. So what is this? So I had a matrix here. Let me bring it back so I don't have to have another one. So there's my C, 2 minus 3, 0, 1. So let's look at, say, 5 times C. What is 5 times C? So 5 times C is the 2 by 2 matrix where I have scaled every entry of C by 5. So 10 minus 15, 0, 5. Okay. All right. Similarly, I could do the same thing for A. So let's do minus 2 times A. So minus 2 times A would be the matrix minus 8, 0, minus 10, 2, minus 6, minus 4. Okay. All right. So that's how scalar multiplication works. Now, couple of things here. So I could use this, so I can use this to define combinations. Right, so A minus 5B, 2 A plus 7B, etc. Things like that. Okay, I'm not even going to write those out. So there's a fact. I'm not even going to write all of the properties. I'm just going to show you. So okay, so let A, B, and C be the matrices the same size. Let R and S be scalars. So matrix addition is commutative. It's associative. You have a 0 matrix, so if 0 is a 0 matrix, A plus 0 matrix, where 0 has to have the same size. They all have to have the same size here. So A plus 0 is A. If you scalar multiply a sum of two matrices, that is what you think it is. There's a distributive property in both slots, in the matrix slot and in the scalar slot. And then this is associative. I can actually do the scalar multiplication first, and then it doesn't matter. This is the same in both directions. Now, scalar multiplication is not the same as the dot product for vectors. No, it is not. It's the same as scalar multiplication for vectors. So a vector is a special case of a matrix. So a vector is a type of matrix. It's a matrix that is just an m by 1 matrix. It's a matrix with a single column. Okay, now, what is really important is matrix multiplication. And when I say really important, I mean really it's like the only operation that you care about on a matrix. So matrix multiplication is the thing. Okay, so what is really the most important aspect of matrix algebra? Is matrix multiplication. Okay, this is by far the most important thing. Okay. Now, how do I define this? So I want to take matrix A and matrix B, and I want to multiply them together to get the matrix product AB. Okay. Now, this is more complicated than those other operations we talked about, but for good reason, because this is way more interesting. The matrix addition and subtraction yield absolutely no useful info. There's absolutely no application of those things, really. They're, like I said, they're basically useless. Matrix multiplication is the exact opposite. Literally everything we're going to do in this course that is worth anything comes from considering matrix products in some way. More or less. So this is very important. Now, it turns out that multiplying two matrices is more involved. And so how does this go? So here is the following definition. Okay, so let's say that A is an m by n matrix, and B is an n by p matrix. We're going to go over this in a second, but this makes no sense unless the number of columns of A and the number of rows in B are the same. This is for defining A times B. As we will see, A times B and B times A are not the same thing. So matrix multiplication is not commutative. It's like one of the first things you notice from it. In fact, A times B might be equal to some matrix. B times A might not even be defined. If M and P are different, it won't be defined, in fact. So basically, you could A times B is defined, and B times A might not even, it might be completely undefined. So this is even worse than maybe something like the cross product that you've seen before in Calc 3. You knew the cross product was an example of a product that wasn't commutative, but it was skew commutative, right? So the only difference was a minus sign. Here, this is totally different. This is just completely not commutative. A times B is equal to something. B times A might be equal to a different size matrix entirely. So that is one thing you note immediately, and I'll talk about this a bunch. Okay, so A is an n by n matrix, B is an n by p matrix. So let B have columns. It has p columns, so B sub 1, B sub 2 through B sub p. Okay, then A times B is A times B written in this way, which we are going to define as the matrix that has p columns, and those p columns are the vector product, or sorry, the products of matrix times vector, which you do know how to do, set up in this way. Okay, that is AB is the m by p matrix whose columns are AB1 through ABP. Okay. So let's do a quick example and then we'll be done for today. So a quick example. So let A be the matrix reading row-wise 2, 3, 1, minus 5. And let B be the matrix 4, 3, 6. And in the second row 1, minus 2, 3. Okay. All right. So then, if we're calling these columns B1, B2, and B3, right? Just checking, A is a 2 by 2, B is a 2 by 3, and so the columns of A match the rows of B, so this is good. And what should the resulting matrix A times B be? It will be an M by P matrix, so it will be a 2 by 3 matrix like B. Okay? Then AB, by the definition, is the matrix A times B1, B2, B3. Right? That is, it's the matrix that is AB1, AB2, and AB3. So I should write out what each of these things are. So what's AB1? AB1 is the matrix 2, 3, 1, minus 5 times B1, which is the vector 4, 1. So how do I write out this product? This is a 2 by 1 vector. Right? How do I do this? Okay, well, I think, okay, this is, I write this as a linear combination where this vector 2, 1 has weight 4, and this vector 3 minus 5 has weight 1. So this is 2 times 4 plus 3 times 1 in the first entry. So that's 8 plus, maybe I should write that out fully. So let's write this out fully. So this would be 8 plus 3 in the first slot. And in the second slot, this would be 4 plus minus 5. Okay. Where does that come from? This is from the definition we have of matrix times vector, right? So this is 11 minus 1. Okay, that's AB1. All right, so what's AB2? So AB2, similarly, is, so A is the same, 2, 3, this is 1 minus 5, and B2 is 3 minus 2. This is 3 minus 2 here. So this is the vector, this is 2 times 3 plus 3 times minus 2, so that's 6 plus minus 6, so that's a 0. And this is 3 plus 10, so that's 13. Okay, and then lastly, AB3 is again A, 2, 3, 1, minus 5, and B3 is 6, 3. So this is 2 times 6 is 12, plus 3 times 3 is 12 plus 9, so that's 21. And then lastly, 1 times 6 plus minus 5 times 3, so that's 6 plus minus 15, so that's minus 9. Okay, and so going back here, AB1 is 11 minus 1, AB2 is 0, 13, AB3 is 21 minus 9, and so this product, AB, is just slopping those vectors in here. So this is 11 minus 1, next is 0, 13, now I'm reading column-wise. 21 minus 9. So that is my matrix product. Now, a couple things to note. One, matrix multiplication is sufficiently complicated that it can be hard to, say, look at product and say, oh, like what matrices did this come from, right? That's too hard to answer. So this is a very, it's a much more complicated operation than those first few we talked about, but it's also the main one that matters. Okay, so we're going to be doing, don't worry about if you didn't get this on the first time through, we're going to be doing this a ton in this class. So I'll do many more examples of multiplying matrices like this. This is just the first. So anyway, do that on Friday. I'll post your homework. It'll be due next Monday. So I'll also have office hours on Monday. I'll try to do that as a general pattern. I'll have office hours the day the homework is due later. So your homework will be due like midnight Monday. And I'll have office hours Monday afternoon right after class. So I'll assign that homework. I'll give you the problem set later tonight. So anyway, I think that's it. So I will see you all on Friday.